So I've decided to make one more video and just dedicate it to Hamiltonian circuits. Okay? What is a Hamiltonian circuit? Let's say we have this graph. Okay? Hamiltonian circuit, or we say that graph has a Hamiltonian circuit. If we can find a circuit, meaning starting at one vertex, going back to the same vertex, where we visit each vertex once and once only. So in this case, it's going to be A to B to C to D to E to F and back to A. Okay? So we definitely have a Hamiltonian circuit in this graph. Okay? We did go through these two edges, but that's fine. Okay? Because Hamiltonian is just about vertices, not about edges. Euler is about edges. Hamiltonian is about the vertices. So this graph has a Hamiltonian circuit. Now, it would have been nice if we had a test that we can see if our graph fulfills that test. Then we know if we have a Hamiltonian circuit or not before we actually look for it. We have similar thing with the Eulerian, right? Remember, with for a graph, if all the degrees are even, then we have Eulerian circuit. If two of them are odd and all the rest are even, we're not going to have an Eulerian circuit, but we're going to have an Eulerian path. If more than two are odd, then we have math. Okay? Now, unfortunately, we don't have the same thing in Hamiltonian. We can't do a test that will tell us once and for all, does it have a Hamiltonian circuit or does it not? What we have are conditions which can give you a guarantee. Okay? What is the difference between that and a test? I'll try and explain. So last year, you were supposed to learn about Dirac's condition. Dirac said, and by the way, it only works when n, the number of vertices, is larger or equal to 3. If each of the vertices has a degree which is larger or equal to n over 2, then we guaranteed Hamiltonian circuit. Let's just find out. So the degree of A is 4. The degree of B, there's 2 vertices, is 2. The degree here is 2. 3, 3, and 2. Now, in this case, what was n? N was equal to 1, 2, 3, 4, 5, 6. There are 6 vertices. So n equals 6. So n divided by 2 is 3. So if each one of these degrees was higher than 3, okay, then definitely I'm guaranteed to find a Hamiltonian circuit. Now I can see 1, 2, 3 vertices with degree below 3. So Dirac's condition is not fulfilled. We don't have a guarantee that there's a Hamiltonian circuit. However, we have a Hamiltonian circuit. We started this lesson with that, okay? There definitely is a Hamiltonian circuit. Now you understand why this is not a test. Dirac condition is not a test. It's just a guarantee. If a graph fulfills that condition, you are absolutely going to find a Hamiltonian circuit. However, if you don't pass this condition, that does not mean you can't find the Hamiltonian circuit. You might well find. Okay? So if I, for example, added another vertex here and another edge. If I added these two edges, now the degree here will change to 3. Here it will change to 3 as well. This one is going to be 4 and this one's going to be 3. Now Dirac's condition is fulfilled. All the degrees are larger or equal to 3. Definitely I'm going to find a Hamiltonian circuit. But as you saw before, even without these edges, I could find it. Okay? Right, so that's about Dirac. Let's look at the next. There's one more condition. Okay, the second condition that we can, a way of figuring out, sussing out if there is a Hamiltonian circuit or not, is called Orr's condition. Okay? So what does Orr tell you? First of all, it's also only for graphs with n larger or equal to 3. I mean, if you have only 2 vertices, well, I guess, that will be a Hamiltonian circuit, and that will not be a Hamiltonian circuit. So really, for n equal to is not a big deal, but for n larger or equal to 3, goes like that. And by the way, I gotta say, okay, maybe a little bit of intro. I didn't see it in the grade 10 textbook. I don't even see it in the grade 12. I saw it in another book, which is AP Math. So I'm not 100% sure you need to know it, but let's just do it. It's not a big deal. I mean, this whole thing about Dirac condition, Orr condition are not huge. It's not a huge part. Mainly when it comes to Hamiltonian, you just need to see if you can find the circuit, and that's it. Okay, so or what did it tell you? It tells you that for each pair of non-adjacent vertices, I need to check each pair of non-adjacent vertices, for example, C and B, means they're not touching each other, they don't have an edge that connects them. The degree of one plus the degree of the other, the sum of their degrees must be larger or equal to n. If that is the case, you got a guarantee from all to tell you you will find a Hamiltonian. So let's have a look, just to kind of explain that. So you've got this graph, okay? In this case, n equal 1, 2, 3, 4, 5. Now, what is non-adjacent vertices? These two are adjacent because there is an edge that leads from one to the other. But for example, B and C are non-adjacent. B and E, this is E, are also non-adjacent. Anything else? A and D are also non-adjacent. I think I've got them all, okay? Now let's calculate the sum of their degrees. So we'll just write down the degrees of all of them. This one is 3, 3, 3, 3, and 2. Okay? So B and C, if I add the degrees of B and C, the sum of degrees is 5. B and E, 2 plus 3 is 5. A and D, 3 plus 3 is 6. So if I'm looking at all these sum of degrees, 5, 5, and 6, they are all larger or equal to n, which is 5. So all will give us a guarantee you're bound to find a Hamiltonian circuit, which, for example, could be A to B to D to C to E to A. Okay? What you're really seeing here is that the more edges we have, I mean, when would this condition be fulfilled? If we have more and more edges, the more edges I'm adding to a graph, okay, that means the degrees are getting bigger. I mean, there's more chance for me to be able to go from one vertex to the other without going back to the same vertex twice, because I've got lots of rows. That makes sense. Okay, let's have a look where OR condition is not really useful. So over here. In this case, I have 1, 2, 3, 4, 5, 6. So n equals 6. Now let's just choose one pair of non-adjacent vertices. Let's say look at B and D. Okay, B and D. Now the degree of B is 2. The degree of D is 2. So the sum of the degrees of those two non-adjacent vertices is 4. Okay? 4. Now 4 is below 6. So OR does not guarantee that we have a Hamiltonian circuit. It does not fulfill OR's condition. By the way, I wrote here, we can say, we'll just leave it. Now, but thinking about it straight, of course I've got a Hamiltonian circuit here. I can go from A to B to C to D to E to F and back to A. Obvious. Okay? So again, OR's condition is not a test. It can't tell you exactly if it's going to be if it will be a Hamiltonian graph or not Hamiltonian graph. If it fulfills that condition, you will have a Hamiltonian circuit. Now, when I say a Hamiltonian graph, I don't think I used it before. When I say a graph is Hamiltonian, it means, okay, what is a Hamiltonian graph? It means that it has a Hamiltonian circuit. Okay, I don't think I used it before. Okay, so Hamiltonian graph is a graph that possesses a Hamiltonian circuit. Both these circuits are Hamiltonian graphs. Both these graphs are Hamiltonian. When I say a graph is Eulerian, okay, that means it possesses Eulerian circuits. Okay? If I say a graph is semi-Eulerian, means that it does not have an Eulerian circuit, but it has an Eulerian path. Okay? So I'll write it down, Hamiltonian graph. I've got Eulerian graph and semi-Eulerian. Hamiltonian means it has a Hamiltonian circuit in it. Eulerian has an Eulerian circuit, meaning it's going through all the edges just once. Semi-Eulerian, it doesn't have an Eulerian circuit, but it has a Eulerian path. Have a lovely day, guys. See you next week.